a URL's journey through the internet. What happens when you type in a URL and then you get a response in the form of a web page, response that you're looking for most of the time? For example, when you type in www.com, in milliseconds, you get the application page, Google's page, that is being returned to you. Building on all previous videos that I've posted on YouTube, I'd like to put together this video where we'll look at different stages through which a URL should pass through in order for you to see the response that you're seeing. There are different ways to put it together through the stages that it passes through. There is a very specific way and there is a surface level flow. And we will look at two different flows which are basically the same if you look into it closely. So there is a client, a user, okay? It can be you, it can be me. When I just type in google.com, I am a client. And the request passes through network. After passing through network, it reaches Google's server. And Google's server sends a response to the client with the web page that client is looking for. Usually it's a HTML page or it can be CSS page depending on the format, but it is in human readable format. So you see Google's page in front of you and you don't care very much what type of page it is. Again, when we enter www.google.com, we get a response, client gets a response, okay? Another way to put this is when you enter a URL in a browser, URL needs to go through a DNS resolution, because when you put together a hostname, example.com, internet, the DNS, the protocols don't understand what you're asking for because it's not in a language that they understand. And DNS's role is to translate it into machine format, which is IP basically. They're looking for an IP and you're achieving this on DNS stage. Then we have a TCP IP stage, which can mean different things depending on the protocol that you're using. And after TCP IP stage, we have routing within the application's infrastructure. So application can be behind the load balancer. It can be behind the CDN, content delivery network. And depending on the architecture of the application, there is routing that to be happened before it reaches the origin or it reaches CDN and you get a response from the origin to the browser. I know it can sound overwhelming at first glance, but I will make my best to look more in depth into it in this video and make it clearer to you by video's end. So when we type something in the browser, nowadays our life is much easier. We can open Chrome, we can open Firefox, any browser, and you can just type in google.com without any consideration for a protocol. But realistically, if you click on a URL on the top of your browser, you will see the full URL, which starts with a protocol. And the protocol is a defining moment in where your URL will go afterwards. So we've got HTTP protocol, which is used less often. You might know that HTTP has usually is on port 80. And if an application doesn't accept insecure traffic, which HTTP traffic is considered to be, it will not respond to you because it will say, I don't accept traffic on HTTP. I have a wonderful video on HTTP. Please check it out if you want to. Then we have more secure and more common option of HTTP, which is HTTPS. HTTPS operates on port number 443. And most of the internet connections are built on HTTPS. If you click on google.com's URL or most URLs that you're trying to access, it can be Wikipedia, it can be Facebook, anything, you will see HTTPS in front of it. And then it can be a local file where you don't have to go through the internet. That file is on your computer. So depending on the file's location, you will have a URL, URN, URI, the link to the object that you're going to access, because that's the high-level definition of it, whether it's on your computer, whether it's on the internet. That's an object that you like to access, and you're using the protocol that is appropriate for that object. File. So sometimes when you download something, a PDF, it can open in PDF application. It can be a preview on Macs, it can be Adobe Reader, or it can be your browser. And sometimes you might seem surprised because, okay, I've downloaded it. Why does it open on my browser? Is it on the internet? But the answer is that it's not. It's a file that is local to you, locally on your machine. It doesn't have HTTP, it doesn't have HTTPS. It's just a file, okay? So here's an example of a link, okay? I'm not gonna get too in depth into different segments of hyperlink. However, if you're interested, check my video about URLs, URNs, and URIs. We've got here a protocol, HTTPS. Okay, here we've got our www example.com, our top level domain, it's called TLD. Okay, so here it's similar to Russian doll. We're building one into another. So we have a top level domain. Here's our main domain example, and here's our subdomain www. So subdomains can change. One of good examples is maps google.com, translate google.com. So Google just keeps changing the domains. Ideally, we explicitly mention the port, but nowadays port has dropped because HTTPS effectively means port 443, sorry. Then we have a path, and then we have a query, okay? That's how a URL looks like. Path and query and everything that comes after is not compulsory, depending on the URL. Now, when we have entered our URL successfully, we are done with the browser stage, okay? We have sent the request. We are now at DNS stage, and this can go two ways. 90% of the time of the use cases, it goes this way. Okay, 90% of the use cases, we're trying to access a resource on the internet. In order to do a DNS resolution, it needs to check through different cache levels before it can define whether it should do a resolution or not. It's similar to us deciding whether we want to buy a new pair of jeans or not. I need to check in my different wardrobes whether I have jeans or not. If I have them, I'm not gonna go ahead and buy a new pair. Why would I need a new pair? And similarly, in this case, before it does a DNS resolution, it needs to check in several places, okay? There are different cache levels for DNS. First is browser cache. Whether you're using Chrome or any other browser, it has its own DNS cache where it stores the information you have already requested. If in the morning you accessed google.com, it noted down that, okay, google.com is on this IP. Next time the client asks for this information, I'm going to show it to him. And that's what happens. If it's present in browser cache, it accesses it there. What if it's not? Then it goes ahead and tries to check operating system resolver cache. It operates in different ways on different operating systems. However, we're going to focus on a more or less common example where you have a resolver cache that might store records for DNS resolutions. If it doesn't find anything here, it checks hosts file. Host file is located in different locations. On Mac and Linux, it's at /etc/hosts. On Windows, it's in another location. But the purpose of hosts file is to trick your local machine into thinking that certain IP is DNS resolution of a certain domain name. So for example, Google's domain IP address is 1.1.1.1. And by entering the record google.com 2222.3, you tell your machine to access 2.2.2.2.3 instead of Google's real IP, which would be 1.1.1.1. So with host file, we can trick your machine into thinking that the website at a certain IP, where it might not be. It's very good for testing something if you need to test and your application, but your application is not publicly accessible, so you're trying to trick your local machine. There are a couple more applications of hosts file, but we're not going to review them on this video. If a host file doesn't have a record about google.com, we are checking the recursive resolver. Okay, recursive resolver is located at your ISP level, Internet Service Provider, in order to find out whether it has the records that you're looking for. If it has the records, if it doesn't have the records that you're looking for, we will go the traditional way to top level domain, okay, name server, which is this, and through name server we'll go to authoritative name server. It's the whole algorithm that it follows in order to locate the records that you're looking for. Think of it as a library. And authoritative name server will be the name server that holds the IP of example.com or google.com. Then you're going to be returned with the record you're looking for, the IP address. But is it usually IP address that you get? Well, mostly yes. You get either a record, which is IPv4, or AAAA, quadruple A record, which is IPv6 IP address. Or you can get a CNAME. CNAME is nothing but a link to another link. So if google.com's CNAME is not google.com, it is a CNAME. And basically what you're doing, you have to look up not google.com now in order to reach the IP that you're looking for. There are a couple of things to consider, among other factors really. It's a time to leave setting. So cache records, whether it's DNS or not DNS, they have time to leave. And what it means is that keep my records for a certain time, but after that point in time, please delete them. Okay? For DNS cache, it's always like that. Time to leave can be 1 hour, it can be 24 hours. For example, if I access google.com and the time to leave for that record is 2 hours, it will be deleted from cache in 2 hours. Another thing to consider is negative cache, which protects us from NX domain attacks. What it does is, there are domains that don't exist. They simply don't. For example, Jama is recording videos on Monday.com. Okay? This domain doesn't exist. So negative cache is nothing but a cache of domains that don't exist. And it's collected on the cache level so that when you ask for that domain, if time to leave is appropriate, it will return the same response, that this domain does not exist, without doing the recursive search and without having to transform it. 10% of the use cases. In 10% of the use cases, the request that we're looking to send is on local network. It's similar like in corporation or it can be in the house. It's a local area network managed by a switch or router that can also act as a switch, which is a more common use case. Therefore, your traffic doesn't have to go on the internet. It doesn't have to go through your internet service provider. It will reach its destination at level 2 OSI interconnect at LAN, local area network, in which case you don't need an IP. If your request is not going through the internet, why would you need an IP? Well, you don't. What you're looking for is address resolution protocol, if it's IPv4, okay, IPv4, or neighbor discovery protocol, NDP, if it's IPv6. Using one of these protocols, you need to get MAC address. MAC address is not Apple Mac. MAC address is the alphanumerical string that is attached to your network interface card. Okay, I maybe put it in a very complex way. Every machine that can connect to network, whether it's internet or local area network, has a NIC, network interface card. Think of it as a part of hardware. And that card has a MAC address. Your phone has a MAC address, your laptop has a MAC address, and if your camera can connect to the internet, it has MAC address. So with MAC address, you can define what machine, what client on the system it should go to. Switch defines it, by the way, using one of these protocols. It doesn't define MAC address, it's hard-coded, but it defines what would be the next hop. If it's not 10%, if it should go on the internet, if it's 90%, it goes to router's default gateway. Through the default gateway, your private IP is changed to default gateway's public IP through network address translation, and it continues through its route. Here, we reach TCP IP stage, okay? So once we're going through the default gateway, we're going through our internet service provider. Our internet service provider can be just one node within the autonomous system, or it can comprise of different nodes on that huge autonomous system. Depending on this, it traverses using IBGP, and then through IBGP, by traversing on the hops within autonomous system, it using external BGP, eBGP, it follows autonomous system path. So it hops from one autonomous system to another to reach the destination. If an application, which I think Google is using, if it uses any cast IP, check out my IP video for more information about it, then depending on your geographical location, your request will be picked up by the POP, point of presence, closest to your geographical location, if it has any cast IP. So if you're in France and there is a data center, the closest data center to France is in Denmark, your request is going to be forwarded to Denmark's data center, Denmark's point of presence. So, okay, imagine we located our path, okay? We located the autonomous system we're looking for, and we traversed through different autonomous systems, and we reached the autonomous system where we should be. What happens then? Then, we're not done yet. We're not even close to being done at that point. It's the time to establish all good three-way TCP handshake, okay? Where it says, hello, okay? And the other side says, hello, I acknowledged your hello. And the other side A, so A, B. Side A says again, I acknowledged your hello. I acknowledge the fact that you told me hello to B. I have a wonderful video about TCP and UDP handshakes. Sorry, TCP and UDP. Once we established three-way handshake, it's time for us. We have established a TCP channel, TCP connection, okay? And throughout this connection, we can now talk to the server on the autonomous system that we're looking for. However, if we're using HTTPS, which is a secure protocol, we also need to establish a TLS handshake. Okay, we need to go through TLS handshake, check the certificates, check the words, check the hash to make sure that everything is as it should be. To check that the server we're talking to is the server that we indeed are supposed to talk to. Once TLS handshake is complete, something else to consider is path MTU. MTU is multi-transmission unit, if I'm not mistaken, and usually in textbooks, MTU is 150 bytes. However, depending on VPN, depending on secure tunnels, depending on the application, certain amount from the MTU size can be offset for headers. That's why the smallest path MTU is considered the smallest MTU on the hops, along the hops on the path, is considered the path in MTU. So if one of the hops MTU has accepts only packets with size of no more than 1400, 1400, it means that path MTU is 1400, and all packets above 1400 will go into MTU fragmentation and will be fragmented during transport. So imagine we have established TCP connection, we have completed TLS handshake, which means that now we can communicate with the application freely. However, after this whole TCP IP exercise, we are now at routing, and ideally, if we pass everything, response stage. Did we reach the application though, when we established the TLS handshake? Well, not necessarily, because the application can be behind different nodes on the system. Sometimes it's a CDN, content delivery network, which basically keeps the certain static and sometimes dynamic content that you can access closer to your geographical location without the network traversing throughout the globe. It can be load balancer, which is also considered a reverse proxy that you can that the request passes through before it reaches origin. Depending on the HTTP version that you're using, I think from version 1.1 we have it already. There will be HTTP persistency, meaning that with one opened TCP connection, you will be able to channel several packets of information. You might ask, but google.com is just one packet, right? It's not quite correct, because google.com as a page has many elements. It has page content, okay, the basic content that we have. It has Google logo, which is another element. It has font. It has any different elements, basically. So we need HTTP persistency to send all these elements through. If there wouldn't be HTTP persistency, you would first get Google logo, Google page, then Google tab to search for something, and it just wouldn't look like how it looks like now. If someone, I remember I was using PCs in early 2000s, maybe end of 90s, then you might remember those times where there was no HTTP persistency and we would get the response in item per item manner. Now, if there is something in front of the application, which usually there is, we have load balancer or we have a CDN, they deal with the request. If CDN can serve the response to you, then it doesn't even reach the origin, okay? The response is returned to the browser. If CDN can't, there is a load balancer that passes your response after checking that response is not malicious. If we have a web application firewall, WAF, it checks for response not to be malicious, and if it's not, it sends it to the origin. And the origin says, okay, it's time for me to respond with a certain web page, google.com. And that's how you get your response back. Of course, in the whole mix, there is also rendering, where your response is parsed according to the language that web application understands. And then, depending on how web application is programmed to work, it puts together a response for you, either in HTML or CSS. Thank you for following all this long way with me. Thank you for using UDP protocol to watch this video. I know the information mostly built on the different lectures that we've covered already, and this video is for intermediate audience. However, I hope we were able to put together different topics that we have covered in the past few months, and it now makes sense how the data packets in the form of URL, as you see it, traverse through the internet to reach the destination and then to send us the response. Thank you for being with me today. Please don't forget to follow my channel, to subscribe to my channel. Don't forget to like my video so that YouTube algorithm is nicer to me. If you're interested in what I do in day-to-day life, follow me on Instagram, let's be friends. And if you have any questions, drop your question in the comment section down below. Thanks for your time today and have a nice day. See you soon. Bye.